So climate sensitivity has been a regular topic of conversation in Climate Change National Forum recently. And here with me today is Dr. Scott Denning, calling in on Skype video from Fort Collins, Colorado, to talk more about this subject. He's the author of the recent post titled Cause and Effect, which is wildly popular, and it goes into climate sensitivity. Just to preface with an introduction, Dr. Scott Denning is the Montfort Professor of Atmospheric Science at Colorado State University. He serves as the Director of Education and Diversity for the Center for Multiscale Modeling of Atmospheric Processes, working to enhance understanding of global climate. And he leads a group of graduate students and scientists using many kinds of observations and models to understand the metabolism of the Earth's biosphere. A key combination of their work is the identification and prediction of sources and sinks of carbon dioxide in the atmosphere using new satellite instruments. And we're going to chat some more about the new satellites with the Orbiting Carbon Observatory, which recently launched. And first off, thank you, Dr. Denning, for chatting with us today. Are you coming in? Am I coming in loud and clear?
Yep, I hear you're fine. Thanks.
So I'd like to start off for people who are unfamiliar with the concept. Could you explain what climate sensitivity is and why it's important?
Sure. We like to think about the climate of the Earth as being driven by or caused by energy coming in from the sun and energy going back out from the Earth out into the rest of the universe. And if there's an imbalance between those two things, if more energy comes in than goes out, the climate warms up. And if more energy goes out than comes in, the climate cools off. So climate sensitivity is really a measure of how much the climate warms per unit energy coming in that's more than the energy going out. So imagine if you were to turn up the sun, a little bit, maybe say by 1 watt per square meter. Climate sensitivity is the amount of warming you'd get in degrees per watt per square meter of extra heat.
And could you expand on this, because this method of explaining climate sensitivity is not what we usually hear, because we usually hear per doubling or the expected warming, equilibrium warming per doubling of CO2 compared to pre-industrial times, which is 280 parts per million, if I'm correct.
Right. So adding extra CO2 to the atmosphere changes the amount of energy that goes out from the surface, to cool the surface. And that is one way that the Earth's climate can change. But there's other ways as well, during the ice ages, a big part of the Earth's land surface was covered with ice, which is very bright, has a high albedo, we say, just means more of the incoming sunshine reflects back out. And that can be measured in watts per square meter, just as the extra heat from CO2 can be measured in watts per square meter. So it's sort of a more general way of looking at climate sensitivity is degrees per watt instead of degrees per doubling of CO2. Mm-hmm. Now, we know that doubling CO2 adds 3.7 watts to every square meter of the Earth's surface, roughly the same as a 4-watt light bulb. Mm-hmm. On every square meter of the Earth. And
that doubling would be at 560 parts per million?
560, but an important thing is that doubling is any doubling. So from 100 to 200 parts per million, that's a doubling. From 200 to 400, that's doubling. From 400 to 800, that's doubling. Each of those doublings is 4 watts per square meter. It doesn't go linearly per 100 ppm, let's say. Mm-hmm. It goes per doubling.
And just to bring it back to just the real basic why it matters context, is we're ultimately talking about the question of how much the atmosphere is going to ultimately warm due to all this extra CO2 that we've added, correct?
Right. Okay. And as I said, the extra CO2 absorbs some of the outgoing long-wave radiation and then re-radiates some of that back down to the surface. So the surface warms when the atmosphere has more CO2, mm-hmm. but that's not the only way the surface can warm. So, for example, if you turned up the sun, not that we have a dial where we can turn up the sun, but if you did, mm-hmm. and you turned it up by a certain amount, climate sensitivity is how much it would warm up per unit extra sunshine or extra radiation from CO2 or extra albedo or whatever. The idea is that the Earth's climate changes whenever the heat in minus heat out changes.
And as you deadpanned, when you add heat to things, they change their temperature.
They warm up. I mean, this is actually, that principle is called the first law of thermodynamics. But as I like to say, you have to be some sort of egotistical Victorian Brit to call something that simple the first law of thermodynamics. People have known about this since the caveman days.
And now you arrived at a measurement of climate sensitivity through this cause and effect framework of about 0.8 degrees Celsius per watt.
Right.
And explain to me how you arrived at this number.
Okay, first of all, it's not me. I didn't just arrive at this number myself in that blog post for the first time. What I'm trying to do is explain a very large body of work.
How do scientists arrive at this number?
Yeah, many scientists. Hundreds of people have worked on this problem for probably 50 years. It actually goes back into the 18th century, into the 19th century. The 1800s was the first time that anybody published an estimate of how many degrees per watt or how many degrees per doubling of CO2. So, but I don't take credit for that. The number, so I tried to illustrate in the blog post 3 different timescales of variation of the Earth's climate in the past that show us the climate sensitivity. I looked at the warming from the last ice age. So maybe your viewers don't know this, but 20,000 years ago, it was a long time ago, right? There were humans on Earth 20,000 years ago. They were painting those cave paintings in the south of France. The Earth was colder than it is today.
And there were woolly mammoths
mammoths and ice sheets and really cold weather over the northern continents. And starting from that point, over 10,000 years, it warmed up by about 5 degrees Celsius. The world warmed up by 5 degrees Celsius. Why? Well, 2 things. One, the ice sheets melted. And when the ice melts, the Earth's surface is darker because the ice is bright and white and reflects a lot of sun. So when the ice melts and the Earth gets darker, it soaks up more sun, so it warms up. The other thing that happened was the CO2 went up a lot between 20,000 years ago and 10,000 years ago.
Which drove which? Or is that still an open question?
Well, I think they drove each other, and same thing with the ice, right? Did the ice melting cause the warming, or did the warming cause the ice to melt? They both happened at the same time, and they happened very gradually. So the temperature rose very gradually for 10,000 years. The CO2 rose very gradually for 10,000 years. The ice melted very gradually for 10,000 years. All these things happened at the same time. And when we add up the extra absorbed sunshine from the melted ice and the extra absorbed outgoing radiation, the thermal radiation from the CO2, it adds up to about 6.5 watts per square meter. So you can divide 5 degrees Celsius of warming by 6.5 watts per square meter, and you get about 3/4 of a degree per watt of warming.
And then you also use other transitions, right? Between the transition between I think it was the medieval warm period to the Little Ice Age, which is not a global event as I understand it. It was just, but it's still, we have good data on that. And then the Mount Pinatubo.
Right. So you can look at sort of climate change on this time scale of centuries instead of tens of thousands of years. So the example there is the Little Ice Age. You can look at climate change on the order of just a few years, where these big volcanoes go off. The most recent one, which I'm old enough to remember, is Mount Pinatubo back in 1991. There was this huge volcano in the Philippines, put all kinds of stratospheric particles in the air, which reflected some of the sun, and the Earth measurably cooled off for a couple of years while these particles were in the air. So all of these different timescales give a very consistent picture of about 0.8 of a degree Celsius per watt per square meter of heating. And if you multiply that number, 0.8 degrees per watt, times the 3.7 watts per square meter per doubling of CO2, you come out with that sort of back-of-the-envelope number of 3 degrees Celsius of warming per doubling of CO2, which is the same number that you get when you sort of do the math and follow the physics all the way through the climate models. They also get right around 3 degrees Celsius per doubling of CO2.
But through this method, you're just kind of looking back in time in these different measurements and
right.
ratios, because you're not, I'm presuming you're not using climate models to arrive at this number.
That's right. You can, so there's as I said, there's probably at least 50 different studies that have been published along these lines, where people have looked at particular climate changes over different periods of time, from millions and millions of years ago, from thousands of years ago, from hundreds of years ago, over the last 100 years, when the volcanoes come and go. All of the data from all these different timescales gives you a value in the neighborhood of 0.8 of a degree. You know, some of them might be 1 degree, some of them might be 0.7, but there's a range right around 0.8 of a degree per watt per square meter of extra heat. The fact that the climate models get that same number is kind of comforting, right? That the fact that the climate models on their own, without using those data, agree with the amount of temperature sensitivity that the Earth has exhibited in the past is comforting. It means the climate models don't disagree with the data, but you don't have to use the climate models to get that number.
And we're actually, there's some pieces in the works that some of the scientists have mentioned about climate models, and I hope to get more into that subject in the future. But bring it back, so this back of the envelope, this 3 degrees Celsius
right.
per doubling, that's looking at the IPCC of the range of 1.5 degrees Celsius to 4.5 degrees Celsius. That's kind of right in the middle of the range of that.
Right in the middle, yeah.
Okay.
So what I'm trying to say is that there are many ways to arrive at that number, and they all seem to give roughly the same answer.
And that's another thing that I'd like to talk about, because I mean I get the radiative properties of CO2, and when you add heat to things, they raise their temperatures obviously. But I mean, how long is this going to take, and why is there such a delay? Well,
the main place that the heat goes in the Earth system is the oceans. I don't know if let's see if I can make a simple argument about that. You ever jump into a swimming pool when it's 70 degrees in the water? It feels kind of cold against your skin. That's because water has a tremendous amount of heat capacity. Water can hold the heat better than your skin can, so it sucks the heat out of your skin to warm up the water. You go outside when it's 70 degrees, or you turn your air conditioner down to 70 degrees, and it just feels comfortable because the air doesn't have as much capacity to hold heat as the water. So water has way higher heat capacity than air. So when you add heat to the Earth, the main place that heat goes is into the ocean. People have measured the heat in the ocean, and give or take, it's 95% of global warming goes into the ocean. Only about 5% goes into warming the air or the land. So when we talk about extra heat warms the Earth, what we're really talking about is that CO2 warms the oceans rather than the air.
But this 3 degrees, we're talking about the atmosphere. We're talking about the air, correct?
We're talking about the average temperature of the air at the surface of the Earth, and most of the surface of the Earth is the ocean, right? So 3/4 of the surface of the Earth is ocean. We don't live in the ocean, right? We live on the land, so we're paying attention to what the temperature is in Colorado or Texas or wherever you are. But you have to remember that most of the Earth is actually ocean, and the ocean is warming by 3 degrees. If the ocean surface warms by 3 degrees, the world is warmed by 3 degrees, and the land will just follow. The heat is mostly going into the ocean. 95% of the heat goes into the oceans.
But the land's a little kind of behind a little bit in terms of...
The oceans are deep. On the average, the oceans are 13,000 feet deep. Imagine how much heat it takes to warm up 13,000 feet of water, right? I don't know if you have a swimming pool, but you know, you have to run the heater for a good long time. And inside your natural gas heater for your swimming pool, the temperature of that flame is much warmer than the temperature of your swimming pool, but you have to leave that flame on for days and days and days to change the temperature of the swimming pool. Imagine the oceans, which aren't the size of your swimming pool. They're 13,000 feet deep. They cover 3/4 of the planet. It takes a boatload of watts to warm up a swimming pool the size of the world oceans. It takes time. You know, we talked about doubling CO2 adds 4 watts. So I don't have the prop here with me, but imagine I'm holding a... Are you old enough to remember incandescent light bulbs? I don't know, Michael.
I believe I am.
Okay, incandescent light bulbs. When I was a kid, we used these little 4-watt light bulbs for Christmas tree lights. When you were a kid, we used these 4-watt light bulbs for night lights to help you find the bathroom in the hallway at night. Imagine one of those little light bulbs on every square meter of the Earth, right? That's going to warm up the Earth. But that 4-watt light bulb will take a while to warm up 13,000 feet of water. It just has a tremendous amount of mass. It takes years to warm up 13,000 feet of water.
But
okay, go ahead.
So the delays due to the oceans, and but correct me if I'm wrong. What are we talking about here in terms of to realize this equilibrium warming? Is it like a few decades? Is it hundreds of years?
Well,
because this is an important policy question, is it not? Because the rate of changes matters a lot in how people can adapt and animals.
Sure. So just like anything else, the temperature of the Earth approaches that equilibrium temperature closer and closer over time. So you make a big change right away, and you sort of slowly ramp, closer and closer to this equilibrium. Here's another example of it. You get out on the freeway with your car and you punch the gas pedal. Your car just doesn't instantly achieve 100 miles an hour. It goes faster and faster and faster, but eventually it sort of levels out. And so putting CO2 in the atmosphere is like punching the gas pedal of the car, but the temperature of the Earth is like the speedometer of the car. It takes a while for it to creep up, and you may get halfway to equilibrium within 10 years. You may get another half of the way in another 10 years, and another half of the way in the next 10 years, and so forth. But of course, unlike with your car, with the CO2, we're continuing to push that accelerator pedal harder and harder and harder. So it doesn't catch up until you stop putting CO2 in the atmosphere, and then after a while, it'll catch up.
Yeah,
it might be 100 years. I mean, think about it like that.
But that kind of,
but not centuries.
Dr. Bart Verhagen, wrote that that's kind of one of the reasons why they call it a super wicked problem, is because those are the most power to do something about it, to reduce emissions, kind of have the least incentive to do so, because they'll be gone. In terms of when the equilibrium warming is finally realized.
So that's an interesting thought, that we don't have an incentive to do anything because we're going to be gone.
This brings in values.
There's a famous book. Why do old people plant trees? Why do you save for retirement? Why do you send your kid to the dentist?
Yeah.
I mean,
and this brings in values.
In all of these cases, you're not going to benefit. Somebody down the line is going to benefit. But we do that kind of stuff all the time.
And that's a values conversation that I hope to highlight and have more in the forum in the near future.
Okay.
Well, thank you so much for your time. But you mentioned the successful launch of the Orbiting Carbon Observatory-2, which I didn't know about. It just happened early July.
Right.
Tell me about this satellite. Why is it? What are we going to learn about it? What is it going to tell scientists? Because I read that it actually might have the ability to monitor carbon down to its actual source on the land, which
that's the point. That's what it's for. So we know how much CO2 is in the atmosphere already. We have 55 years of measurements from the top of the mountain there in Hawaii, Mauna Loa, which are excellent in terms of tracking the CO2 in the atmosphere year to year, month to month even. We wouldn't need a satellite to do that. All you need to do is have an instrument out there in the atmosphere. What the satellite is intended to do is monitor tiny little changes in the amount of CO2 from place to place. So let's just say it makes a daily map of CO2. That's a little bit of an exaggeration because it's really just skinny little stripes wherever the orbit of the satellite is not a full map. But you could sort of imagine that there might be a lot of CO2 downwind of Beijing, right? Because there's this huge amount of emissions. So you see this kind of plume of CO2 going out from China. And on the other hand, you might imagine that there's not as much CO2 over the Amazon because it's sucking up CO2 to make trees. So by using these maps, what we're hoping to do is map out the places that CO2 is being emitted and the places that CO2 is being soaked up by the oceans and by the land.
And just curious, does this go into other greenhouse gases like methane?
No, this satellite will only measure CO2 concentrations, not methane concentrations. There's some other satellites that measure methane, carbon monoxide, other things.
Cool.
But here's what you may not have heard. Only half of the CO2 emitted by burning fossil fuels stays in the atmosphere. Only half. So half of the CO2 that's been emitted through the whole history of the Industrial Revolution, burning coal and oil and gas, half of that CO2 is gone. Where did it go?
Dissolves into the ocean, right?
Half of the missing carbon, half of the carbon that's not in the air is in the ocean. We can find it. We got measurements in the ocean. We know where that is. But that means that the other half of the missing carbon has to go into the land. And that was a shocker. When I was in graduate school, that was the first time that scientists really kind of came to grips with the fact that half of the missing carbon is going into the land. And the reason why that's a surprise is that it's not enough to just have photosynthesis taking CO2 out of the air. What we're saying when we say half the CO2 goes into the land is that the growth of new plants is more than the death of old plants. Things are growing faster than they're dying across the world, which was really a surprise. Almost all ecologists, forestry people, so forth, before that discovery, thought it was the opposite. They thought stuff was dying faster than it was growing. They thought that tropical deforestation, plowing the prairie, cutting down the forest to build suburbs, all that stuff was on the net turning plant material into CO2. But they were wrong. On the net, the CO2 is actually turning into plant material. And we really would like to know where that's happening, how that's happening, whether it'll keep happening, whether that carbon that was taken up from the atmosphere by the plants is going to come back anytime soon. So that's really what OCO2 is all about.
Cool. Because, I mean, that is possibly a good thing, right? If it's enhanced ability for the plants to, absorb more of it, great.
Right.
But in terms of...
Think for a second, we're getting roughly a 50% emissions reduction for free by the oceans and the land. Wow.
However, the oceans, that also brings up the issue of ocean acidification, right?
That's right.
Which is
CO2
not a good...
in the oceans dissolves, things in the oceans, which is a problem.
Yeah.
On the other hand, CO2 into the land and the atmosphere means there's less CO2 in the air by half.
Interesting.
So it's a big deal.
Well, fascinating discussion, and hope to explore more of these topics and branch out from there. But thank you for your time chatting with us today, Dr. Denning, and thank you for contributing to Climate Change National Forum, and hope to hear more about this OCO2 in the future.
Great. You're more than welcome. Nice to talk to you.